All right, so in order to define moment of inertia, I'd like to go back to our original definition of inertia. If you recall Newton's first law, an object in motion wants to stay in motion, and an object at rest wants to stay at rest, and unless acted on by some external force. That's what we called inertia, right? This tendency to resist a change in its motion. So the moment of inertia of an object for rotation is simply the tendency of an object to resist rotating or to resist angular acceleration. And so just like in linear terms, when we had an object that had greater mass, we said that that object had greater inertia. In other words, it was more likely to resist a change in its motion. So similarly, objects with larger moments of inertia are harder to rotate or more difficult to start or stop rotating. So in this way, the moment of inertia of an object is just the rotational version of mass. And so instead of using mass when we're solving problems dealing with rotational motion, we're going to use this moment of inertia concept instead because it helps us not capture just the mass, but also how that mass is arranged. It takes the symbol of a capital I. We'll come back to the units of measure in a moment. If you look at the bottom of this slide, you'll see the equation for calculating the moment of inertia. And so let me break this down for a second. This sigma is just talking about a sum. And then what we're doing is we're adding up. Imagine that an object were made of a million small little points of mass, almost like atoms, if you will, right? It's as if we took the mass of each one of those points and multiplied that mass by the distance from the center of the object squared. And so what this is saying is add up every single little point mass on an object, take the mass of each point and multiply it by the distance of that point from the center squared. And what this is saying is you would do that I times, where I is the number of points. So if there's a million atoms in an object, you would do it for every atom or really every point mass. Now this can be incredibly tedious, and we'll see on the next slide that we actually have equations developed already for standard shapes. But the idea is correct here. The moment of inertia is proportional to the mass and how far that mass is placed from the center. And so you notice because r is being squared here, as you increase the distance that mass is placed from the center of the object, we're increasing the moment of inertia exponentially. And so what we can actually do is we can apply that to this example here on the right-hand side. Let's say that you have a disk on the left and a ring on the right. Now, the difference between a disk and a ring is that, let's say these both have the same mass total, okay? The disk is a solid, continuous surface, whereas the ring has a hole cut out of the center. If they each have the same mass, then we don't have to worry about that being different. But it's clear to see that their mass is not distributed the same. So if I think about the disk, this is the center of the geometric center of the disk. And then every single point, I'm just going to draw a bunch of points, right? These would all be little points on the disk, and I can keep going out, and there's no end to how many of these I could draw, right? If I were to take each one of these points, find the mass of that point, and then measure the distance from the center, and did this for every single point, right? That's what this equation, this sum of mr squared is trying to tell me. That's what I'm doing there. But I notice now for the ring, right, none of those masses start until we get out here to this inner radius. So if I go ahead and I'm just going to call this r here. This will be the inside radius of the ring. All of my mass begins at r and is between r and little r and capital R. So in this region, in this band, if you will. All of the mass is in this outside region. And so you can see here that for each term, right, this r squared is going to be a bigger number for the ring. Because the ring is distributing all of its mass far away from the center, the ring is going to have a much greater moment of inertia than the disk will. So if we think about a million points on the ring, since all of the points are far away from the center, they will all contribute more greatly to what we're going to say is a larger moment of inertia. So the disk here is going to have a smaller moment of inertia, and the ring is going to have a larger moment of inertia because the ring positions its mass farther from its center. Again, they both have the same total mass, but the ring distributes that mass farther away from the center, the geometric center of the ring, which would be, again, right here in the middle, or the center of mass, if you will, if we go back to our previous lesson on center of mass. Both of these objects are symmetrical and have a center of mass in the middle, but they don't distribute their mass the same way. All right, and just to kind of wrap this up with the units of measure, if you see that the equation is m times r squared, just all those added together. Mass is in kilograms typically, and then radius here is a distance that would be measured in meters, so meters squared. So the units, no surprise here, kilogram times a meter squared. There's no name for this unit. We're just taking the unit of mass and multiplying it by the unit of distance squared. So a kilogram times meter squared is the standard unit for the moment of inertia of an object. All right, now we don't need to deal with this sigma sum equation anymore. We're going to take a look at the next slide where we'll see a lot of already determined equations for standard objects. All right, so this slide gives you the equations to calculate the moment of inertia of various geometric shapes given how they're being rotated. So let me walk you through this in a little bit. This solid cylinder right here, this is one type of shape. Okay, and we're told that the axis of rotation is through the center of the cylinder. So you see this red line here, this is the axis of rotation. That would be the axis around which we're actually rotating the cylinder. If I have a cylinder like this, I can calculate the moment of inertia, I, by taking 1/2 and multiplying it by the mass of the cylinder, capital M, and multiplying it by the radius of the cylinder squared. And the radius would be, again, this point from the center out to one of the edges. That would be my radius that I'm going to plug into that equation. So that constant, this is a constant right here. You'll notice a pattern as you see these. Each of these equations looks almost the exact same. I equals some constant times capital M, capital R squared. So we can almost think about it like I equals K. You just leave K as some constant. And really, the trick is, what is K? And that will be given to you. You'll never be asked to determine what K is. In this class, you'll always be given what K is. So if we're given a solid cylinder, I would tell you, the moment of inertia is 1/2 mr squared. This is just a constant that has been determined from the previous equation for this known shape. So this works the same way for all of these objects. A hoop is like a ring in 3 dimensions. That would be just mr squared, no constant. The constant is just 1 here. A solid sphere would be 2/5 times the mass times the radius squared. A rod about its center, so this is a rod where the axis is through the middle of the rod, is 1/12 m times, and L here is not the radius, but you might imagine it's the length of the rod, a bit different, but same idea. And then on the bottom row, we have a bunch of the same objects, but just if we have a different axis of rotation. So let's say if the cylinder instead wasn't going through the center, but I stuck it like through the side of the cylinder in the middle, it would actually be this whole thing, this 1/4 mr squared plus 1/2 ml squared. Similarly for a hoop, again, if we put now the axis of rotation not through the hoop, but through the side of the hoop, we would have a different equation. A thin spherical shell. So a shell is different than a sphere. A shell is like hollow inside. So that's what the word shell means. The sphere itself is hollow. There's just a thin material on the outside that has a thickness that we maybe know or maybe don't know, but it's hollow inside. So it looks a bit different. And then we have a rod where you attach an axis to the end of the rod. Now, what I want you to notice as well is how the constant changes based on how the mass is distributed. Which of these objects do you think is the most dense or most solidly arranged object, right? If you look at these moment of inertia equations, remember, right, the bigger the moment of inertia, the farther away from the center of the mass is distributed. So I'll write that out. And so you can see here that, let's compare the solid sphere and the thin spherical shell, just for example. You'll see here that the constant for the solid sphere is 2/5, right? But the constant for the thin shell is 2/3. Well, I know that 2/3 is bigger than 2/5, right? So the moment of inertia for the thin spherical shell is going to be larger, right? This mr squared doesn't change, assuming same mass, same radius. The moment of inertia for this thin spherical shell is greater than the solid sphere. And that's because the thin spherical shell distributes more of its mass on the outside than the solid sphere does. And so we see that the constant gives us an idea about how the mass is distributed as well. So this kind of concludes our series of videos on moment of inertia. This is just an introduction. We will be using the moment of inertia much more in this unit when we are looking at different kinds of quantities, when we look at torque and its relationship to acceleration in the next series of videos. So please go ahead and continue moving on, and thank you for watching.